Hello, everybody. In this tutorial, I will give in first video, I will give some summary of the Laplace transformations. And the second video, I will do simple examples. And the last video, I will give some examples on the applications of the ordinary differential equations. So Laplace, what is the Laplace transform? It's defined for a function from 0 to infinity, for a real valued function. And Laplace transform of the function f is another function fs, which is an integral exponential. S is the variable for this function, e to the minus st ft dt. So it's an indeterminate integral. That is the definition. Sometimes we denote this function as L of ft's, saying that L is a linear transformation, is a transformation for the functions. I will explain a bit more about that. How we know the existence of the Laplace transform? There are some conditions for the existence. Not every function this integral makes sense. That's what I mean. So if we have a function which is locally integrable from 0 to infinity, which means that this integral is finite for any a is for a finite number. So this is what it means, locally integrable. If it is not locally integrable, and if there exists a constant, positive constant, c, b, gamma, satisfying this condition, then Laplace transforms exist. We can talk about the fs. So, and we can write fs as a bounded functions of this integral plus this quantity. What is happening as a summary of the definition? We have all functions. We have the set of all functions. That is a vector space, right? As a vector space, if you're thinking about the functions over the real numbers, also all functions will give you a vector space over the real numbers. Then L, the transformations that we define, a function, a map from the set of all functions to the set of all functions. If this is too large, so we cannot define all the linear transformations for whole function. If we restrict, as it happened in this theorem, we talk about only locally integrable functions and some finiteness condition as we have given here. And if we restrict that vector space into that subspace, then apply the Laplace transform, we obtain an equivalency. So this the sort of function goes to that kind of functions over there too. And we prove, the theory tells us, L is one-to-one surjective, which means there exists an inverse function. So we can go from that spot to that spot. So these kind of functions, the set of all these kind of functions, are equivalent to this kind of functions called the transformation L. What the theory tells us. What it means, L also is a linear. So S is a linear transformation one-to-one and surjective for the functions satisfying these conditions, or among the functions satisfying these conditions. So what is the idea behind the Laplace transform? Why we bother? Well, the thing is that the idea is that if something is very difficult to solve in here in this space, we would like to apply to the L transform here, Laplace transform here, and do the calculations here when we come back, and hoping that, of course, the calculations or computations is a lot easier in this, or possible to do it, probable to do it here, and then we will go back and then find a solution here. So that's the idea. And this idea is used, this kind of idea is used in mathematics in many different places. So if something is difficult in one space and we try to find out the equivalent space, that we can do the calculations and then we go back with the similar formation, similar transformation, similar functions, or similar functional to go back and to do the calculations in the first one. So that idea is used a lot, and Laplace transform is one of them. Okay, let's keep going for the summary. What was the linear means? Linear means you have a constant, a function, plus another constant, another function. So we can write the constant Laplace transform of the function plus the constants goes out, and the addition can be split. So what it is, A and B are the real numbers. But this is true for the addition. Don't confuse with the multiplication. If you have a multiplication, if you have a multiplications of two functions here, that you cannot split from the, you cannot split that at all. So this doesn't work for the multiplication. Works addition. That's what linearity means. Okay, and the gamma function, this is just a definition because we give Laplace table, Laplace transform table about the gamma function. So this is why we define the gamma function. Gamma function is defined as an integral exponential minus x to the gamma minus 1 dx. And this is a very famous function. It is a special function in mathematics, and it satisfies these properties. We are going to say one of the, if you have the function t to the nu is a real number, then the Laplace transform of this will be given by a gamma function divided by s nu plus 1. So how we do the calculations instead of having done all these things? So what we do, we looked at certain type of, functions here, of course satisfying these conditions, put here, calculate it, and make a table. So that will make us a lot easier to use the table for the calculations. So this is how we get the table. We have long table, and even some sources will give you a larger table. So these are the functions, and these are the Laplace transform when you obtain it. Since you have an inverse transformation also works, so inverse Laplace transform of these functions gives you this one. So it is not one way, it is both ways. So this one gives you this, Laplace inverse will give you this. Laplace gives you this, Laplace inverse give you this. Okay, and that's how it goes. So so t to the mu, Laplace transforms of t to the m, m is a natural number including 0. So t to the 0, for example, will be 1. So 0 factorial is 1. So S0, 1, so it will be 1 over S. So the t, L1 will be just 1 over S. T will be 1 over S squared. Okay, so it is basically 1 will be, maybe write it down, L1 is m is equal to 0. So this is 0 factorial, which is 1. So this is 1 over S. And for example, L of t will be 1 factorial, which is 1 over S squared, and so on and so forth. Okay, so this is what it means. M is a natural number. Could be 0, 1, 2, and so on. If we have an exponential functions of this kind, Laplace transform is this, sine, Laplace transform will be this, and W is a constant here, and T is the variable. And similarly, yeah. So what is ut minus a here? I will give a definition of this function here. So ut minus a is the Heaviside function, which is the ladder function. So what it means, we have before a, if you have an a here, before a you have 0, and this is not included. Then you have 1 over 2, so this assume that 1 over 2, and then you have 1, which is which is again empty in that point, but continues after that. So this is the function ut minus a in this function is here. And Laplace transform is exponential minus as over s. TGT here is the Laplace transform of this kind is the negative of the Laplace transform of J derivative. So G, the big G here, is the Laplace transform of G. This is how it looks. And the by here, prime here, means the derivation. So we are taking derivative of this. So that's the table. It will be much more clear when we are doing the exercise. Okay, if Laplace transform of f is, this is about the theorem that I was talking about the linearity and about the one being one-to-one and surjective. So L inverse existence of L inverse. I can ignore this two line. If you want to read later on, you can read it. The effects of ut minus a, this is just a summary. Ft ut minus a cuts the function f. Ft minus a ut minus n shifts and cuts. This has been done in your lecture, so I'm not going to do the extended so much. Shifting theorem is extremely important. You have to know this. You don't need to know the tables, but you need to know how to use it. We will use it often. You will see it in the practice how we use it. Okay, this is what it means. The Laplace transform of f is given by the big F is, and this is the first shift. So this is the Laplace transform, it's the inverse. So both of them are the same thing. They are both equivalent, either this one or this one. So the e to the, if you have an exponential function in front of your function, it gives you a shift by a in the function, in the big SF function. Or another way of, so the shifting means is basically, is this part. So this is the independent variable for the function. S is independent variable for the big F function. So S plus A is the shift, means you are putting S plus A whenever you see S in that function. That gives you a shift in terms of the dynamical system. Okay, if you have Ft minus A, Ut minus A type, and then the that, as we say, it gives a shift and cut. This Laplace transform of this function will be just a shifting with the exponential functions of Fs. These are important for us. 1 and 2 are important for us when we are doing the practical work on that. So when we are applying the Laplace transform into the ODEs, and these are the equations that we usually use, right? If Laplace transform of the function f is denoted by fs, and the derivative of the f, and we are taking the Laplace transform, will be sfs minus f0. This f0 is the initial condition is given in the question to us. So we get used to do such questions for the variable y. So if it's a second derivative, we have this. The first derivative, we have this. And when we are using it when we are solving the ODEs by using the Laplace transform, it will be easy. It will be clear. So how the procedure goes, I just wanted to list how we solve ODEs by using the Laplace. We take Laplace transform of the ordinary differential equations. We we use these equations that we've listed here. Then we use the initial conditions, which is f0, f prime 0. These will be the numbers in that case, because initial conditions means f0 is something, f prime is 0 is something, f2 prime is 0 something, right? These are the initial conditions. And then we solve the equation ordinary differential equations applied to the Laplace, and we have an algebraic equation, which solve the algebraic equation for our function fs, of course. And fs is equal to something, that's what you're going to find out. Then we apply the inverse Laplace transforms. When we apply the inverse of this, we will get f, which is the solution. And in that way, we are omitting the general solution for the ODEs. We don't need to calculate the general solution for the ordinary differential equation. We directly calculate the particular solutions by doing the Laplace transform trick. Okay, this is the list of this, what I gave it to you. And this is a quicker list to see, to make the things quicker. So this is equivalent to things that I've seen. And yeah. So this is a shift for A, right? And yeah. So these are the quick way to use this. They're basically not only that I'm using the tables, but I also use to get those ones with the shifting. Okay, let's do some exercise. I will stop this one here, and then the next video I will start doing exercise. Thank you very much.